AI can generate a Selenium script in seconds. But can that script understand your framework, follow your application patterns, compile successfully, and survive engineering review? That is the problem I want to explore today. Hello, I'm Balaji, a test architect with more than 20 years of experience in software testing and quality engineering. I've seen testing evolve from manual execution to automation frameworks, continuous testing, and now AI-assisted engineering. That experience led me to design ATAP, the AI test authoring platform, an approach that takes AI-generated automation beyond code generation and toward dependable engineering delivery. This funnel shows where the real challenge exists. At the top, the market is crowded. Many AI tools can convert requirements into test cases. Move down the funnel, and fewer tools can convert those test cases into Selenium scripts. But a generic Selenium script is not yet usable automation. The funnel narrows significantly when the code must adapt to your framework, your page objects, reusable components, coding standards, naming conventions, and application architecture. At the narrowest point is the real test. Can the generated code compile, satisfy engineering standards, and be safely delivered? That is the last mile of AI test automation. Most tools concentrate on the crowded first mile. ATAP was architected specifically to complete the difficult last mile. The answer did not begin with an AI model. It began with the complete testing lifecycle. I worked across every stage shown here: planning coverage, designing business scenarios, architecting frameworks, implementing automation, reviewing code, and maintaining test suites over time. These stages are connected. A weakness in planning affects design. Poor design creates weak automation. Ignoring the framework produces duplication and brittle code. Compilation failures create review rework, and every shortcut eventually becomes a maintenance cost. ATAP mirrors that real engineering lifecycle. It starts with the business scenario, studies the existing framework and application context, generates code within established patterns, applies deterministic validation, performs a real compilation, and attempts controlled repair when failures occur. The validated change is then presented to an engineer through a pull request. ATAP is not intended to replace the test engineer. It is designed to bring an architect's discipline into the AI authoring process. ATAP makes three important engineering commitments. First, it stays in sync with your stack. The generated code conforms to your framework and application instead of forcing your organization to change its architecture for the tool. Second, it does not assume that plausible-looking code is working code. The output is structurally validated and passed through a real compile gate. Third, deterministic guardrails inspect the result. When the AI makes a mistake, ATAP detects known failure patterns, attempts bounded repair, and validates the code again. The principle is simple. The model proposes, but the platform verifies. If ATAP cannot establish the required quality, the code does not move forward. 5 architectural pillars make this possible. Framework. Agnostic adaptation protects the automation investment you already have. Multi-LLM orchestration provides model flexibility and reduces dependency on a single provider. On-device capability supports privacy, offline execution, and cost control. Guardrail and compile verification provide evidence that the generated code meets engineering expectations. Finally, human control delivery keeps the engineer accountable for the final decision. ATAP creates a pull request for review. It never force merges AI-generated code. Together, these pillars balance acceleration with reliability, security, and governance. This diagram can be read from left to right. Every AI request first enters a provider. Agnostic gateway. Behind that gateway, ATAP can work with Anthropic, OpenAI, DeepSeek, Gemini, or a locally running Ollama model. On the right is task-aware routing. Framework discovery, code generation, scope analysis, and AI-assisted repair do not necessarily require the same model. Each task can be routed to the provider and model best suited to its quality, cost, performance, and privacy requirements. The gateway normalizes the differences between providers. If a fallback would send information to another provider, explicit consent is required. This provides multi-model flexibility without silently giving up control of your code. For organizations where source code cannot leave the environment, ATAP can run the AI generation process locally through Ollama. This provides the four benefits shown here. The code remains on the machine, there is no per token cloud cost, generation can operate without a cloud connection, and framework content is not shared with a third-party module. The important point is that local AI is not a separate demonstration mode. It participates in the same ATAP workflow, with the same validation, compilation, repair, and human review controls. Architecture becomes meaningful only when it works in a real engineering workflow. So let me show you the whole thing running end to end. Watch four moments in particular: how ATAP is configured, how it reads an existing framework before it writes anything, how one plain English sentence becomes framework aligned, Selenium code, and what happens at the compile gate when that code is finally put to the test. From configuration to a review-ready pull request, here is ATAP in action. Step 1. Connect. Before ATAP writes any code, it needs two things: the application under test and the existing Selenium repository it will contribute to. First, I name this run a test suite. I'll call it home page verification. Next, the application under test. Here, the Nook Commerce demo site, the running app the generated test will actually run against. Then, the GitHub repository, my existing Selenium framework. The codebase ATAP reads, extends, and opens a pull request into. It builds from the base branch, main. But instead of touching main, it creates its own working sub-branch, so your main branch is never at risk. With that set, I click Connect and Validate. It runs four checks. 1. The application is reachable. 2. The repository is accessible. 3. The base branch exists. And 4. It can create a working branch and open a draft pull request. All four pass. Nothing has been written yet. This just confirms the ground is solid before we start. Step 2. Framework analysis. It clones the repository into an isolated workspace and reads the entire project, never modifying your repo. First, it confirms this is a usable Selenium framework. Then it maps the architecture it found: feature files, step definitions, page objects, and shared support, all built on top of the Selenium WebDriver. It pins down the exact stack: Java 17, Selenium 3141 Maven, and Cucumber on the page object model. That's how it knows to write code that fits this project, not a generic template. It even learns your conventions: how you locate elements with find by, how you assert, how you report. It reads the code base the way a careful new engineer would. And most importantly, it finds the components already there to reuse. Existing page objects like home page and login page, so the generated code extends what you have instead of duplicating it. Step 3. Test scope. This is where the test begins, and it begins in plain English. I describe what I want, the way an analyst would write it. Verify the home page loads, and the header shows the search box, the register and login links, and the menu. This is meant to come straight from a Jira story or a Confluence page. No test design syntax required. I deliberately keep the number of cases small here, capped at a handful, so AI usage stays cheap while I'm demonstrating. I take generate, and a local model running on my own machine turns that one sentence into structured test cases. Step 4. Test cases. Here is what the model produced from that single sentence: fully structured, editable test cases. Each case has concrete steps, the exact locators it will use, and the expected result for every step. It even makes its assumptions and risks explicit. Nothing is hidden, so I can trust what I'm approving. If I want a change, I don't hand edit. I describe it in plain English, and the AI revises the case for me. I review, and I approve the case I want. Only the approved cases move forward to code generation. Step 5. Navigation, preview. Before it writes a single line of code, it walks the proposed steps of the test. I can step through each action and its expected result. If something is off, I pause, correct that step, and resume. The correction is saved straight back into the test case. It's a dry run of the logic, so problems are caught before any code exists. Step 6. Code generation. Now it writes the actual Selenium code for the approved case. It produces 3 files: a cucumber feature, a step definition class, and a page object. Exactly the structure your framework already uses. And it reuses what's there, the existing base driver and hooks, instead of reinventing them. It shows me precisely which architecture layers changed. Here are the real files with real diffs. This is framework fitting Selenium, not a generic snippet. If I want a change, I describe it in plain English, and it rewrites the files, grounded in my framework. But generating code that looks right isn't the hard part. Proving it actually runs is. Step 7. Validation. This is the heart of it. It applies the change to a throwaway copy of the repo inside an isolated container. Then it runs the framework's own build. Dependency resolution, a real compile, and the test executed against the running application in a real browser. This is the compile gate. Nothing moves forward unless the code genuinely builds and runs. No hallucinated success. Dependency resolution passed. Compile passed. Test execution passed. Everything green, including a real browser run. Step 8. Delivery. Only now, after it is proven to work, does it offer to deliver. And even here, a human is in the loop. I acknowledge that I've reviewed the diff and that I accept the validation results before anything is written. On approval, it creates the working branch, commits the files, and opens a draft pull request. It never merges and never pushes to your base branch. And here it is on GitHub. A real draft pull request opened by the tool. It contains the 3 generated files, the objective, the validation result, and a clear note that human review is required before merge. This is the actual diff in the actual repository. The tool's output ready for a normal code review. I'll close it here since this is a demonstration. Before I finish, the engine room. This is task-aware model routing. I assign a provider and model to every workflow task independently, and every operation reports the exact model it used. I can mix local models on my own machine with hosted ones like Claude, GPT, or Gemini, with an optional fallback used only when the primary is down. Keys are encrypted, and a least privilege GitHub token handles the pull requests. Finally, the final report. An end-to-end record of the whole run. The framework it analyzed, the scope, the cases, the generated files, the validation evidence, and a full audit trail, including anything it honestly could not execute. That's ATAP. Plain English in, compile verified Selenium out, delivered as a reviewable pull request, with real guardrails and a compile gate at every step. What you have seen today is not simply AI generating test scripts. ATAP represents a controlled engineering approach to applying AI in real-world test automation, where the model first understands the existing framework, works with real application elements, follows established coding patterns, and proves that its output can compile and execute before anything is delivered. The key principle behind ATAP is simple. AI should accelerate engineering without compromising quality, security, traceability, or human control. ATAP converts a business scenario into structured test cases, framework-aligned automation, validated code, and finally a review. Ready GitHub pull request. When the generated code fails, the platform attempts to repair it. When it cannot guarantee quality, it stops the delivery rather than pushing unreliable code into the repository. This is the difference between using AI as a code generator and architecting AI as a dependable engineering capability. Through ATAP, I wanted to demonstrate how my experience in test architecture, automation engineering, framework design, and quality governance can be brought together to solve one of the most practical challenges organizations face today: adopting AI without losing engineering discipline. Thank you for watching the demonstration of ATAP, the AI test authoring platform.